talk is by Matthew Nethercote from University of Cambridge. Acoustic wave diffraction by a doubly periodic water square lattice.
Hi, I just want to quickly test the pointer because it wasn't working earlier. Okay. Hi, so before I start, just want to say a quick thanks to Anastasia and Gennady for allowing me to kick off this workshop. Means that I get my talk done and over with straight away. So the problem that I'm going to be talking to you about is a multiple scattering problem involving a full quadrant of scatterers. This is work that I've been doing with Anastasia and Raphael. So I'm going to be talking about two different methods that we've used to find a solution here. Both of them use the discrete Wiener-Hopf technique, but in different ways. So let's set up the problem. So we got a full quadrant of scatterers making a quarter lattice, and each of the scatterers in this lattice position, so it's doubly periodic and infinite in the positive x and y directions. The scatterers are also equally spaced, so this quarter lattice is also a square lattice. We're looking to solve for the acoustic pressure field, and the scatterers themselves are, well, in 3 dimensions, they are infinitely tall sound-soft cylinders. So we're going to have Dirichlet boundary conditions. Each of the scatterers, they're all identical to each other, so they're going to be cylinders of a radius given by A, and like I said before, they're equally spaced with a spacing given by S. We use this vector Rmn to describe the location of the center of the scatterer in the mth column and the nth row. We need to make sure that these scatterers are not intersecting or overlapping in any way, so we need the radius and the spacing to satisfy this inequality to make sure that doesn't happen. We're looking for time harmonic solutions to the linear wave equation. So by assuming and suppressing this time factor, we can reduce our governing equation to Helmholtz's equation. And lastly, the incident wave that we're considering here is simply a non-skew plane wave. So I've given it here using cylindrical polar coordinates, and it's also depending on 2 parameters, k being the wave number and theta I being the incident angle. And I'm also restricting the incident angle so that it's such that the wave is incoming only from outside the lattice. So to start, we're going to be following the same procedure as was done in these 2 papers. We're going to assume that the scatterers are small in comparison to the wavelength. What this means is that we can liken these scatterers to isotropic point scatterers, and as a result, so we're going to be using and abusing Foldy's approximation in this work. So what this means is that each of the local scattered fields of each of the scatterers is going to have no dependency on a local observation angle, and that means that they are simply going to be a product of an unknown scattering coefficient and a local Green's function. This case being Hankel's function of first kind at 0th order. This means that the entire scattered field is going to be a summation of all these local scattered fields for every single cylinder. So this makes a monopole expansion. And then the total wave fields we can decompose into incident and scattered wave parts. So the objective is clear. We need to find these unknown scattering coefficients. So what we do, we can apply the boundary conditions and approximate for small scatterers to create a system of equations that looks like this. And what we do is we looked at this system and we thought that's too hard. So what we tried to do is to simplify things by decomposing the lattice. And it's at this point where the two methods I'm going to talk about are going to differ. So by decomposing the lattice, what the result of that will be is that this two-dimensional sum here is going to be split into two parts. Part of it is going to stay on the left-hand side and become part of the discrete Wiener-Hopf kernel. And the rest of it is going to be moved onto the right-hand side and become be treated as forcing. So for the first method, we split this lattice into an infinite series of rows, and equivalently we can do the same thing but split it into columns instead, but without loss of generality. We're doing rows in this talk. So what this means is that if you were to imagine that we're focusing on this blue scatterer here, then on the left-hand side of this system, we want to keep all the terms that are associated with the same row. So each of these red scatterers, I want to keep them on the left-hand side and move all of the others to the right-hand side. And this is the result of that split. So here, interaction between all the scatterers on the nth row in this case. Here we got forcing due to the incident wave, and here we got forcing due to any incoming waves that are scattered from all of the other rows. So we use as I mentioned, we use the discrete Wiener-Hopf technique here, and in the interest of time, I'm not going to go through like all the details, but suffice to say that the procedure is not that much different from what was used for semi-infinite array problems, and this was described in those two papers that I mentioned earlier. The only real difference is that here we've got this extra term to deal with, but it's not that much more difficult. But long story short, in the end, we can write the solution in the form of an infinite matrix equation. So a bit of notation, these bold letters here, they represent column vectors of scattering coefficients, specifically for the nth row. And you can see that this is an implicit solution, and it's also split into two parts. So this first part here is the part of the solution that you get if you were to assume that that row is completely isolated. So if you imagine just ignoring all of the other rows, then what you're left with is a semi-infinite array problem. That solution is what this is. This other part adds in the interaction between all of the other rows, and it's highly dependent on these like interaction matrices. In theory, we're supposed to have an infinite number of these equations. This big Q here is supposed to be infinite, and the sizes of all of these vectors and matrices are supposed to be infinite as well. But in reality, we can't compute an infinite number of coefficients, so we need to introduce some sort of truncation. And when we do that, we do it in such a way that we're trying to work out all the scatterers for a lattice that is as wide in the x and y directions. And And with this, what this will do is it'll limit the number of equations. It'll make this Q finite, and it'll limit the sizes of all these terms. And what we can do with that is we can take all of these equations and we can reformulate and piece them together. This will form one giant matrix equation, and then it's just a matter of inverting this matrix, and we've got our solution for the scattering coefficients. So we published a paper on this work last year, and I spent a good deal of time trying to find an effective means of comparison between this method and more numerical methods, so we can see how well it performs. And credit to Stuart Hawkins and Dave Hewer, who I don't think are here this week, but yeah, they helped me out a lot with finding this effective means of comparison. So we did this for a whole bunch of test cases, and so for what I'm showing you here, so we're looking at the real part of the total field. We're choosing a specific quarter lattice, and we're choosing incident waves at 3 different frequencies. And the reason behind this is because we're wanting to pick frequencies that should be in stop bands and other frequencies that should be in pass bands. And that is it. It was kind of guesswork from looking at the fully infinite lattice that we chose these. So the top row is using this Wiener-Hopf method, and for sake of simplicity, I've given it an acronym of MSIA, or multiple semi-infinite arrays. And this bottom row is the numerical method we compared with, which was a least squares collocation method. And in these cases, I've chosen quite a fairly low truncation number, and you can see that these two are agreeing quite well to the naked eye, at least, despite this low truncation number. So now on to the second method that we're working on. So again, focus on this same blue scatterer, but instead we want to keep the terms associated with these red nearest neighbours on the left-hand side and move all of the others onto the other. And this is the new system of equations that we will get. So how we deal with this is, so we use one-sided two-dimensional Z transform to transform this system of equations into a new Wiener-Hopf equation. So a quick rundown of the terms. This A++ is the transform of all of the scattering coefficients, and this is the function that we're needing to find. This B1+ is a 1D transform of the coefficients on the boundary of the lattice, specifically the horizontal boundary. B2 is the same thing, but for the vertical face, and this A00 is there to cancel out duplication in the coefficients. Lastly, this F++ is the transform of the forcing terms. And it's important to note that this is including incident wave forcing and incoming waves from non-nearest neighbour scatterers. We also get 2 kernel functions this time. So this K tilde, you can imagine it as sort of a truncated version of the two-dimensional discrete Wiener-Hopf kernel. And this, and we've also got this L kernel as well. The only real thing of note for these kernels is that they satisfy so the same symmetries as a normal discrete Wiener-Hopf kernel does, Notably, if you replace z with 1 over z, for instance, you get the exact same thing. And a similar thing with zeta. So how we tackle this, so I'm going to be using a method that Anastasia recently published, and this was on a more general Wiener-Hopf problem where we have 2 complex variables and 3 unknown functions, which is perfect for us. That's exactly what we've got. And the idea of the method is to define a manifold that is the set of z and zeta points such that this truncated kernel is 0. So that involves solving a quadratic equation. So we're going to get 2 solutions. First one, which I've just called m, and the other one being its reciprocal. Now what this will do is it will eliminate one of the unknowns, notably the a++, and then we get 2 simplified Wiener-Hopf equations, which we can then add and subtract to eliminate more unknowns, and then this is the result. So now we have a reduced Wiener-Hopf equation that's got one complex variable and has got one unknown function. And solving this is can be done with fairly standard methods. We looked out because now we don't have a kernel to factorize. That's usually the bane of everybody's existence. But we do have to do some splitting. But long story short, once we find an answer for B2, we can then find B1 and A++, and then it's just a matter of using the inverse 2-dimensional transform, and we've got our scattering coefficients. So I've written this solution in using suffix notation here. Now originally this MA term was actually, it was one term. The coefficients were embedded in there, and we originally didn't know how to separate the two. So our original idea was to try to create an iterative scheme from this, but that was where our luck ran out, because this iterative scheme kept diverging on us. So we tried again to separate the coefficients, that ended up succeeding this time, and we get quite a similar matrix equation to what we had before, except we've got double the dimensions to deal with now. And this is quite difficult, well, for me at least, to try to formulate and solve a matrix equation like this in MATLAB. So what I ended up doing was using a cheeky trick where I essentially just reshaped the data to reduce the dimensions of the terms. So, for example, if you imagine for this term, that is a 2D matrix, but imagine squashing all the column vectors down. So this matrix, so the matrix columns basically become a single column vector of column vectors, if that makes sense. And for the 4-dimensional tensor, we reduce it so that this 4-dimensional tensor becomes a 2-dimensional block matrix. And again, in theory, these are supposed to be infinite in all directions. So this one is supposed to have an infinite number of blocks, and each of the blocks is supposed to be infinite. But we're going to need to introduce some sort of truncation so we can use this practically. And we do so such that we got the same number of scatterers across in the x and y directions in this lattice. And what that will do is it'll make each of these blocks square, and we'll have a square number of blocks. And then it's just a matter of creating this the new matrix equation, which we can formulate and solve using elementary matrix arithmetic. So the good thing about showing you those previous graphs is that with those other two methods agreeing on what the solution is supposed to look like, we have a goal on what we're supposed to get with this new method. So I've done the same thing here. I've taken the exact same cases and I've compared the real part of the total field in this, and you can see again with a low truncation number, they agree quite well to the naked eye. In the paper that we're working on, we've also been looking into trying to compare the coefficients more directly, and a couple of ways that we do this. One is to literally look at the absolute difference between each of the scattering coefficients using the different methods. The second way is to take our result for the scattering coefficients and actually substitute them into our system of equations to see how well it solves them. And I don't have time to show you all of them because I will run out of time really quickly. But there are three main takeaways. The first is that each of these methods work better for smaller wave numbers. And this kind of makes sense because each of them were built using Foldy's approximation, so it was kind of expected. The second takeaway is that the error tends to be more focused towards the truncated ends of the lattice. And needless to say, if we increase this truncation, then this error improves. So, we should be converging to a true solution in the limit as the truncation goes to infinity. And the third takeaway is that when we substitute the coefficients into the system of equations, we find that this new method satisfies them the best, and the old method satisfies it the least best. And yeah, so the last thing that I want to talk about is what I'm currently working on, and so this is a question that I've been asking myself, which is, can we use the scattering coefficients to gain some information about the effective wave numbers of the quarter lattice? So what I've done here is I've plotted, so I've taken the stop band case and I've plotted the the absolute value of the scattering coefficients along a series of rows for the left one and a series of columns for the right. And what we find is that in this stop band case, the coefficients are exponentially decaying up to a certain point, and then the absolute value becomes constant. And this kind of makes sense, because if you picture yourself at picking a particular row or column, you're at the edge of the lattice. As you progress along this column or row, you'll get deeper and deeper into the lattice. So this accounts for the exponential decay, and you keep on doing this right up until you hit the diagonal of the quarter lattice, and then your new nearest edge is not where you came from, but the other one. So then you're running along parallel to that, so you're not going deeper into the lattice anymore. And we do this we've shown this for all three methods, and we find that only so the new method and the least squares collocation method agree quite well with finding this behavior, but the old method of split into semi-infinite arrays doesn't capture this behavior very well. And we see this again if I were to do something a little different, and instead of plotting along rows or columns, but instead go along the diagonal of the lattice. So in this case, we're always progressing deeper into the lattice, so we should always have exponential decay. And you can see the splitting up into semi-infinite arrays doesn't work as well. Any other thing of so reason why there's two of these graphs, even though it's the same case, I've taken two different truncations here. So the one on the left, I've taken a truncation at 25, and the one on the right, I've taken one at 50. And you may notice that I'm only showing you the first 60% of the coefficients. And this is because there's around about this point that the truncation starts to have a bit of a negative effect on capturing this behavior. So you can see that starting to happen right here. But if you look at this one where I've doubled the truncation, that arrow is completely gone. So yeah, so we're quite satisfied with what we've done for the stop band cases. We're also wanting to try to look into pass band cases to see if we can do a similar thing. And so far, this has been quite difficult to interpret because I think this one is a lot more sensitive to the truncation. So I don't really have much else to say on that other than it's a work in progress. Okay, so to summarize, we looked into a multiple scattering problem with a full quadrant of sound-soft scatterers. We found a solution using two different methods that both use the discrete Wiener-Hopf technique. We've compared the two against each other as well as against a third numerical method. And we found that despite the fact that these methods are quite independent from each other, they agree very well. And we've also been looking into the behavior of the scattering coefficients to see if we can glean any information about the effective wave numbers. There are numerous avenues which we could go down to further this work. The key task right now is to finish this investigation into effective wave numbers. And I think this is going to be important for trying to link this work with the equivalent homogeneous wedge. I also think that the code that we use, the MATLAB scripts that we use for this new method can be improved. Because right now it's not optimal, and it shows because of the three methods, this new one is the slowest. But I think that there are ways to improve its efficiency using asymptotic expansions. And lastly, we can also try to expand this method so that we include more layers of nearest neighbors. And I think that this will lead to some very interesting mathematics, although not quite sure at the moment if there will be like a cost-effective benefit when it comes to computing the final solution. And reason for this is because it's going to be a lot more complicated, and chances are that will translate into the MATLAB scripts. So yeah, it'll be interesting, but got to find a way to justify it as like a legitimate method for people to use. And that's all I have to say, so thank you for listening.
Thank you very much. We have some time for questions, please.
Yes, thanks, Matthew, for this very nice talk. I was just wondering how important is basically the edge, right? Because I'm guessing, like generally speaking, the field will be dominated by the edge when you're close to the edge, and will be dominated by the basically infinite periodic lattice when you're far away from the edge, right?
Yeah,
maybe
right.
Sort of like leverage this idea somehow.
Yeah, I think so too. Not particularly sure about like how much of how do I put this? How much of an effect that will have, how important that will be. But yeah, I think I think that will be important. That's important to consider. Yeah.
Can I comment on that?
Yeah.
If you show your numerical results, it's on slide 6 and 12. Let's look at 12. Now, if you look at the top right-hand corner of the 4 pictures on the right, you see very clearly a semicircular wavefront in each case,
Yeah.
which is centred at the bottom at the corner.
Yeah.
So clearly what's happening there is the field is dominated by a circular wave centred at the corner.
Yeah.
So you know in advance what its form will be. It'll be 1 over root r times the function of theta,
Yeah.
which is the directivity. Now the reason I mention that is that in a different area involving Wiener-Hopf, you normally get this analytically from Wiener-Hopf, and the particular source I know about is Weinstein's work. It's a totally different application area, but invariably he was a wizard. Given the Wiener-Hopf solution, he would invariably work out its asymptotics, and in that context he would compare it with, say, the Kirchhoff approximation, and he would give very accurate description analytically of what the errors were in the approximate methods. But I just wondered if you considered that approach.
This was actually another reason why we would try to look into these like effective wave numbers to see it, especially for like these ones. So like we're not sure if it's purely a cylindrical wave or if it's a cylindrical wave at first that then becomes a plane wave as it goes further on.
Well, based on similar problems,
or even like for like the continuous wedge, we could get headways in this. So I'm not sure if that plays a role as well.
I would say almost certainly it is very closely a wave which comes from the corner, and I simply say that by analogy with many other examples where you have a corner. This is what happens in the far field. And it's amazing, really, given the overall complexity of the problem. That's really all there is. I mean, it will obviously not be accurate near the edges themselves, but if you're some distance away, not very far, that's all there is at leading order. It's remarkable.
Yeah, I agree.
Thank you. Please.
In the two-dimensional Z transform, when you derive the equation and look at your kernel function,
So
do you make, or do you see if you can make a connection with the lattice Green function for the quasi-periodic lattice Green function for the infinite array, periodic infinite array?
I think when we first looked into this to try to, we originally tried transforming this one, and I think the kernel you get from that is I don't know if it is or if it's at least very associated with the periodic Green's function.
The reason I'm asking is because if you can make this connection, and it should be possible, then many things related to convergence will be sorted out. Because if you look at evaluation of doubly periodic lattice Green's function, you will see that there are quantities known as lattice sums.
Yeah.
And some of them, although you can write them nicely, some of them are very tricky.
I know how to use them for the one-dimensional kernel, but I struggle to try to get that to work for this one.
There is plenty of literature, and in particular, the Australian school has done a lot of work on this. I mean, Ross McFedron, Klein Nikarovich, Bolton, Chris Bolton, and colleagues working with them, and of course Leslie Gridgard. And there is a book on lattice sums, and it addresses these things. But of course, chronologically, it goes back to Raleigh.
Yeah.
So it's Raleigh's paper goes back to 1892, and he treated it in a very, very effective way. So, when this connection is made, you will see that many issues of the convergence will be resolved based on the previous analysis of lattice.
Yeah, thanks. I'll look into that. Yeah.
Thank you very much. Please.
Thanks, Matthew, for your talk. Just one comment is that I sort of wonder whether the circular wave will only exist near the edge. Far down the lattice, it'll have to be something else, right?
Yeah, I think it depends on situation you're in. So. Yeah.
What is numerical calculation? How did that was a numerical calculation done here. How big was the lattice?
Oh, so yeah, so with these, I had to keep the truncation number quite low, but I used, so I came up with enough coefficients so that it's 50 wide and 50 tall. I can probably get as far as 100 by 100, but I think and maybe 200 by 200, but I think by that point I'm running out of RAM. So, but yeah, in these ones it's 50 by 50. But yeah.
So thank you very much. I'm afraid we leave all other questions if there are any to discussion section. Thank you very much